Okay, so let's continue this idea of writing equivalent radical expressions. We also call this reducing radicals because we're putting it in a more reduced form. But this time we're going to have some variables thrown in there. So we have a key piece of information that helps us with when we're square rooting variables. The square root of x squared. We need to remember what the square root of x squared is equal to. Square rooting and squaring are opposite operations, like multiplying and dividing will undo each other, adding and subtracting will undo each other, while squaring and square rooting will undo each other. So if I'm taking the square root of x squared, that's going to be equal to x. You can square root an x squared and see how we have x and we have taken the square root. All right, so we're going to come back to that idea. Let's write an equivalent expression for the square root of 63x to the 9th. So we are going to first focus on the fact that there's a 63. And we're going to think about our perfect square factors. Maybe we'll write them off to the side again. Well, you guys probably have them in your notes in the last example, but 4, 9, 16, 25, 36, 49, 64, and so on and so on. Does 63 have a perfect square factor? I think we did this one in the last example. It does have a 9. So 9 times 7 is 63. And then this x to the 9th power, we're going to break that up into perfect square factors. Well, an x squared is a perfect square factor because we can square root it perfectly. So we're going to rewrite x to the 9th with x squareds. So, and this is the long way, by the way. I'm showing you the long way so it makes sense. And then we'll find kind of some shortcuts through this a little bit. How many x squareds does it take to get to x to the 9th? So I have 1, 2, 3, 4. We have 5, 6 x's so far. Another x squared gets us up to 8. And then we need one more x to get to 9. All right, so what I'm going to do next is I'm going to look at everything that's underneath the square root and figure out what we can square root. Well, we can square root a 9. That was our perfect square. Square root of 9 is 3. The 7 we cannot square root, but I can square root this x squared. Remember, the square root of x squared equals x. So the square root of this x squared is x. The square root of this x squared is x. I'm going to sound like a broken record. The square root of this x squared is x. The square root of this x squared is x. And when we are square rooting just an x, we don't have enough x's to square root, which is why that is going to stay underneath our square root. Everything down here I have taken the square root of. So everything down here is going to go out in front of our radical. We have a 3 times x times x times x times x, which is 3x to the 4th power. And then anything that we were not able to square root stays underneath the radical, 7x. So this is an equivalent expression. It's actually a reduced radical for square root of 63x to the 9th. All right, what do you guys think of that? So we're essentially just breaking down into factors and finding the perfect square factors that we can actually square root. All right, so square root of 25x to the 3rd. So let's rewrite that. 25, well, that is a perfect square. But x to the 3rd, we're going to rewrite with x squareds. X squared times x. There's our x to the 3rd just broken down. All right, so what can we square root? Square root of 25 is 5. Square root of x squared is x. And then that x stays underneath the square root. So our final answer is going to be the 5 times x out front, and then the square root of the x that was left underneath the square root. We didn't have enough x's to take that square root. All right, so next one, we're gonna shortcut this a little bit because I can see there's an x to the 17th power. I don't want to write out a bunch of x squared, so I'm just going to think about it in my head. But let's recognize there's a 5 out front, and then we're looking at the square root of 4 times x to the 17th power. Well, 4 is one of our perfect squares, so the square root of 4 is 2. And now this square root of x to the 17th power. How many of these x squareds, like we did up here, can fit into x to the 17th power? By the way, if our exponent is odd, we're always going to have a leftover x. If our exponent is even, we'll be able to square root, we'll have a perfect number of x squareds. So how many x squareds can we fit into x to the 17th power? And hopefully you're saying, well, there's 8 of them. Right? If there's 8 of these x squareds, every time we square root one, we get an x. Every time we square root one, we get an x. We would have 8 of these x's down here that we could square root. So that's going to be an x to the 8th power after square rooting it. I'm going to cross this off and say that we are going to have an x left over underneath our square root. This 5 that caught my eye comes down. So all of these things are going to be in front of your square root. So 5 times 2 is 10, x to the 8th power, and then the square root of this guy was left over. We did not have enough x's to square root that last one, so square root of x. And we'll go over this in class, kind of this way to shortcut. But feel free to write out all your x squareds. Just when I have such a large number of them, I personally don't want to write those out. So think about it in your head and you will get 8 of these x's after square rooting, and you can just jump right to the x to the 8th power.